Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about how not to predict an election. This video was inspired by the 2016 US presidential election, which happened the first year that I was teaching Probability and Statistics. You might remember that Hillary Clinton was heavily favored by the prediction models, but then she lost. Part of the reason why this happened was because there were certain independence assumptions within the prediction models that happened to not be very accurate. Today, we're going to delve a little bit deeper into this and try to explain first why these independence assumptions are even necessary, and then what effect they can have on the prediction of an election. Let's take a look. We're going to see how not to predict an election. The goal is actually to illustrate some important considerations in probabilistic modeling. Okay, so how does the United States presidential election even work? Well, it's an indirect election. We don't just count the number of votes, and whoever has the most votes wins the election. In fact, if I remember correctly, I think Hillary Clinton had more votes. So what happens is that citizens of the US cast ballots for electors in the Electoral College. And those electors are the ones that choose the president and the vice president. How does that work? Well, each state gets a number of electors that is proportional to their members of Congress. So large states such as California get more electors, smaller states such as Delaware get less electors, and Washington, D.C. gets 3 electors. And then all electors in a state are assigned to the candidate that wins that state, except in Maine and Nebraska, where we do something slightly different. So if you want to predict the election, and this is, for example, what 538 does and other other people that try to predict elections, they use poll data to predict the probability that candidates win in each of the states. These probabilities would be, for example, equal to 1, so we can represent them by this random variable, not the probability, okay? So we define the random variable that candidate A wins in state I. So typically in US presidential elections, there's just 2 candidates. So this makes modeling a little bit easier than in European elections. So here we're going to have this random variable VI that is 1 if candidate A wins in that state and 0 if the other candidate wins. And now we need to aggregate those results to estimate the outcome of the election. So if we ignore Nebraska and what was the other one? Maine, I think. Let me check. If we ignore Maine and Nebraska, how can we do this? Well, we multiply each state by the numbers of the electors in the state, and we check whether that number is greater than half of the total electors. If that happens, then candidate A wins the election. Okay, so now we just have to see what's the probability that this random variable is equal to 1. How can we compute this probability that we're interested in? Well, we need the joint PMF of these guys. All right, so computing the PMF of the outcome of the election requires estimating the joint PMF of what happens in each state, because then that's what we're going to multiply times the number of electors and see what's the probability that more than half of the electors will choose candidate A. If you have seen the previous video on Bayesian modeling, there we were more focused on this question, on can we figure out what the probability is that a certain candidate wins a certain state. In particular, we were looking at what was the probability that Trump won Pennsylvania in the 2020 election. Okay, now we're looking at another problem, which is how do we aggregate all those probabilities to produce a final prediction for the whole election, just to make that clear. Okay, so this joint PMF that we're talking about, how many entries does it have? Each state, in each state, we can have 2 possible outcomes, 0 or 1, depending on whether candidate A or B wins. So the number of possibilities is 2 to the power 51 minus 1, that's 10 to the 15. Even storing this joint PMF is problematic. Forget completely about estimating it from data. This is going to be absolutely impossible, no matter how many data you have. What is this? This is the curse of dimensionality. We have a joint PMF of 51 variables, no way we're going to be able to estimate it. We're going to have to incorporate independence or conditional independence assumptions, as we saw in the video on the curse of dimensionality. All right, so what if the outcomes in each state are independent? Okay, then we're in business, right? Because how many parameters do we need to estimate? We just need to estimate the marginals. There's one parameter per marginal, so this is just 51 parameters. So that's great. That looks amazing, right? So what could go wrong? Well, what could go wrong is that you could end up with a really bad prediction because the independence assumptions might not hold. And we're going to work through a very simple example that enables you to understand a little bit, that hopefully will show you why this could be the case. So we're going to consider a cartoon US election where there's still 51 states, but to make our life easy, all the states are the same. They have one elector each. So whoever wins more states wins the election. And now we're going to, again, define a random variable vi for each state that tells us whether the Republican wins or not. And the result of the election is basically the result of the election is equal to 1 if more than half of these guys, so more than 25 of these 51 variables, equal to 1. So the sum is greater than 25. If that happens, the Republican candidate wins. E is equal to 1. If that doesn't happen, then the Democrat wins. E is equal to 0. We want to compute the probability that E is equal to 1. So using some poll data, this is completely made up. I just want to make this clear, just to illustrate otherwise we wouldn't see the forest for the trees, right? If we were looking at a real US election example, it just gets too complicated. So that's why we're looking at this cartoon example. So we imagine that using poll data, we determine that the fraction of rural voters voting for the Republican candidate is 60%. And the fraction of urban voters voting for the Republican candidate is 10%. This reflects the fact that typically in big cities, people tend to vote less for Republicans. What's the problem? The problem is that the turnout of rural voters on election day is uncertain. This actually captures something that I didn't know about before I read a little bit into predicting elections, which is that one of the main challenges when you try to aggregate poll data in order to figure out who is going to win an election is figuring out who is going to turn out to vote. Like knowing what certain sectors of the population, like what fraction of them would vote for a certain candidate, is not that difficult. It's much more difficult to figure out if they're going to go out and vote or not. So to reflect this, we're going to model the turnout of rural voters. We're going to model the turnout as a uniform random variable in 0, 1. Okay? We don't know how to model it. Well, we don't know how to model it. Like in this hypothetical scenario, we believe that this is a good model for the turnout. First, we're going to begin with an assumption where the turnout is independent. So whether the rural voters go out to vote in Alaska is independent with whether the rural voters are going out to vote in California, let's say. Why do we need this independence assumption? Because otherwise things are intractable due to the curse of dimensionality. All right, so now we're going to compute the probability that condition on a certain turnout. Oh, actually, yeah, we're going to compute sorry, I don't know what I was thinking about there for a moment. It's been a very long day. So condition on a certain turnout, what is the probability that the Republican candidate wins state I? Well, remember that 60% of the rural voters vote for the Republican and 10% of the Democrat voters vote for the Republican. So then if this R represents the fraction of rural voters, and that's what it represents in our model, then the fraction of people that are going to vote for the Republican is going to be 0.6 times R plus 0.1 times 1 minus R. So here you see very quickly that if more rural voters go out to vote, then the Republican candidate has a better chance. If less rural voters go out to vote, then they have a smaller chance of winning. All right, so what is the probability that the Republican candidate wins in state I? What are we going to do? We're going to use this conditional PMF and also the fact that we know the marginal PDF of the random variable Ri, which we're assuming is uniform. Okay, so how do we compute this marginal? We have a video on this about the joint distribution of discrete and continuous random variables. We take this proxy for the joint distribution of continuous and discrete random variables, which has the marginal PDF times the conditional PMF, and we integrate it over the continuous PDF. So now here we're going to plug in the marginal distribution of the continuous PDF, which is just uniform. And here we're going to plug in the conditional probability of winning that state given the value of R, which is exactly this. So we integrate that quantity. Notice here this is 0.6 R minus 0.1 R. That's why there's 0.5 R there. That always confuses me. Now we take that integral. It's not too difficult. It's equal to 0.35. So this is the probability that the Republican wins an individual state. And because this is a cartoon election, this is the probability for all of the states. Okay, we have set up the problem so that it's as simple as possible. Great, but that's not what we're interested in, right? What we want is the probability that they win the whole election. So under our assumptions, this probability is the same for all the states. Now we ask ourselves, what's the probability that they win the whole election? We're assuming that the turnouts in each state are independent. So an immediate consequence is that the probability that they win in each of the states is also independent, just by our assumptions. So now, what is the distribution of the number of ones that we're going to see in these 51 Bernoulli random variables with this parameter 0.35? Just a binomial, right? So this is a binomial with parameters n equals to 51 and theta equals to 35. So now we just sum all the probabilities from this binomial being equal to 26 up to 51, right? So what's the probability that the election, this random variable that represents the election, is equal to 1? That's the probability that this binomial is greater than 25. So that's why we sum it from 26 to 51. And the probability that we get is 1.4%, very small. Okay, so under this assumption, essentially what is happening, the Republican needs a lot of rural voters to come out to vote, but when a lot of rural voters come out to vote in Alaska, in the other states, they're not coming out to vote. It's difficult, because they're independent. The probability that they all come out to vote at the same time is very low, so the probability that they win the election is very low. Okay, this is driven by this independence assumption. However, is the independence assumption reasonable? So, thinking, for example, about the 2016 election, it just happened that in the Midwest, the predictions were wrong in the same direction quite systematically, which might indicate that something like the turnout of certain rural voters or some other kind of voter that supported Trump, or the lack of turnout for some urban voters that might have supported Hillary, was not taking into account. And in particular, what was not taking into account is that they could be correlated in the same direction. So we're going to try to incorporate that assumption within our model. Now, what we're going to say is that the rural turnout R is shared across the states. Okay, so it's going to be the same. The same fraction of rural voters are going to go out to vote in California, Alaska, Hawaii, all at the same time. Okay, this of course is a cartoon situation. In reality, you would probably have higher correlation in states which have similar demographics. Okay, but again, we don't want to make the example too complicated, so we're going to look at a situation where they're all correlated. Okay, how do we incorporate this? We're going to say that we still need conditional independence assumptions, by the way, because otherwise we're completely lost. We have this joint PMF of 51 states. We cannot estimate it in general. That's completely impossible. So what we're going to do is we're going to incorporate conditional independence assumptions. This is like what we explained for Markov chains or naive Bayes. We have to wisely choose our independence assumptions. In this case, we're going to say that the outcome in the different states is conditionally independent given the turnout. So we fix the turnout, then the outcome is independent. Excellent. So let's go on. Conditioned on a certain value of the outcome, what is the probability that the Republican candidate wins an individual state? Well, the turnout R is still uniform 0, 1. If we take an individual state, what are we going to do? We're going to do the same as before. We're going to compute this conditional PMF of winning that state given R. It's still exactly the same. We still have the same assumptions for that individual state. The marginal distribution of the individual states is exactly the same. The probability is still going to be 0.35 that the Republican candidate wins each individual state separately. The only difference within the model is that now these guys are not independent. They're conditionally independent given R, but they do depend on the same R. Okay, so under this alternative model, let's compute the probability that the Republican candidate wins the election. We want the probability that E is equal to 1. For that, we basically integrate the conditional probability that E is equal to 1 given R over all the possible values of R. Now, what is this equal to? This is equal to this event that the sum of the states won by the Republican candidate is greater than 25, conditioned on the turnout. And this is very important. So now here is where we're going to incorporate our assumptions. We're saying that all of the states share the same turnout, and conditionally on that turnout, they're all conditionally independent. Okay, so, maybe I'll just show you. What is this? Conditionally on the turnout, what's the probability that the Republican candidate wins a certain number of states? Is just binomial with a parameter equal to, maybe I should have kept this here, like the parameter is equal to this, right? Like this is the probability of winning each state conditioned on R. All of those are conditionally independent given R. How many of them are going to be equal to 1? That's just a binomial with this parameter and n equal to the number of states. Okay, so that's why here we have this binomial that we're summing from 26 to 51, okay? Because that binomial is the conditional joint PMF of the outcomes in the different states given the rural turnout. And the most important thing is that the rural turnout is shared. We will see now that this makes a huge difference. So now we need to compute this integral. It turns out that you can actually compute this because it happens to be a beta function. But imagine, and this is going to happen all over the place in Bayesian parametric modeling, that we don't know how to compute this integral. I don't know how to compute this integral. How could you approximate the value of this integral if you don't know how to compute it? This is another very important topic in practical probabilistic modeling. So what you do is you just simulate this guy. You simulate the random variable E. You simulate many times, and then you count what fraction of times it equals 1. How can you simulate that random variable? You have to incorporate all of the assumptions. So this is the Monte Carlo method. You can check out our video on the Monte Carlo method. It's used all over the place in probabilistic modeling because often these probabilities cannot be computed by hand or explicitly. What we're going to do is we're going to simulate many elections. Now we're going to generate the rural turnout Rj. We can do that, right? Because we can generate it. We know it's uniform between 0 and 1. We just generate it. Whatever, it's 0.6, let's say. Then conditioned on that value, on 0.6, we generate the result in each of the states. We know the conditional probability that the Republican candidate wins in each of the states, conditioned on that value of the rural turnout. So we simulate it. We aggregate the state results and see if the Republican candidate wins in more than 25 of the states. If they do, then we set this guy equals to 1. And now we do this n times. We compute the fraction of times that this guy was equal to 1. And this is going to give us a very good approximation, if n is large, to this integral. Okay? And this is how we often compute probabilities in practice in probabilistic models. All right, so what happens if we do that? What happens if we do that is that we go from 1.4 probability of the Republican winning the election to 20%, so 20 times more. Why does this happen? Well, the logic is that if the rural voters go out to vote, and this is dependent in the sense that they go out to vote in all of the states, if they happen to go out to vote, then the Republican has a good chance because they're going out to vote at the same time. Within the independent model, the problem was that when they were going out to vote in California, they were not going out to vote in Illinois. In the alternative model, there's this dependence, which is captured by the alternative model, where they go out to vote at the same time. And if that happens, it gives the Republican candidate a chance of winning the election. And again, this captures to some extent some of what happened in the 2016 election. Just to finish showing you the results, this is the conditional PMF of the probability that the the Republican candidate wins under the independence assumptions. We see that it's very peaked because of these independence assumptions. The model that includes dependencies is much more spread out. So when we look at the probability that the probability of being to the right of 25, approximately there, then the model with dependencies, maybe I should put it in blue, has much higher probability. Okay, it has much more uncertainty because of the fact that the rule turnout is dependent. Hopefully that makes sense. All right, so what have we learned? We have learned about some very common ingredients for practical probabilistic modeling. We have seen that we have seen how to model an election where basically you try to figure out who's going to win in each of the states and then you aggregate them, and that's how real prediction models such as the one from 538 operate. We saw that Monte Carlo simulations are absolutely crucial because when you have to compute some probabilities within the model, very often it's not tractable to do this by hand. And again, this is used all over the place in practical modeling, including the 538 predictions. And finally, we saw that independence and conditional independence assumptions are absolutely crucial. And the problem is that they're very necessary because otherwise we fall into the curse of dimensionality and we cannot estimate anything. So we need to make some independence or conditional independence assumptions, but we also need to be aware that they can dramatically affect our prediction. And that's all I got. Thank you very much.